Hey guys, we're going to be doing a quick cover of forces and get started with an introduction to pressure. So I'm going to try to work through these notes. These are the same ones we did in class, but I wanted to put the video here so that you guys have it available that you can go back and look through. And I'll try to record them as we go through them in class in the future. If you have any advice or you want something different, I need you guys to kind of give me a heads up. And if that's the case, send me an email. Let me know what you want to see a little bit differently. And I don't know, we'll keep trying new things. So please let me know and work with me. So, number one, we need to discuss what is a force. And a force is designed as any push or pull. So, if you push on the wall, you are applying a force to it. It doesn't matter if it moves or not. All that matters is if it's being pushed or pulled. And forces are measured in newtons. And 1 Newton is equal to the force required to push a 1 kilogram object and give it an acceleration of 1 meter per second squared. And again, any individual force will not necessarily cause an acceleration because there might be other forces that cancel it out. But that's what a Newton is the amount of force required to move a 1 kilogram object, to accelerate a 1 kilogram object and speed it up 1 meter per second every second. And that's what I mean by meters per second squared, meaning it would get 1 meter per second faster every second. 1 Newton is the weight of about 1 apple. So again, applying that to the previous thing, that kind of gives you a feel for what a Newton is. The weight that it was required to hold up a small apple is 1 Newton. And whenever you work on a problem, you should first do a diagram called a free body diagram where you label all of the forces on the object with arrows. So you might have normal force or force of gravity, and we'll discuss those other forces. Maybe there's an applied force, and maybe there's air resistance. So whatever forces are acting on it, and all of the forces acting on it, you should label all of them in the problems as you get to them. So give some examples of forces. Again, this is any push or pull. Kicking a soccer ball, gravity pulling you down, air resistance pushing back on you as you're trying to run a marathon. Anything that pushes you or pulls you in any direction is a force. And as we go through the year and you guys get more and more practice with this, you'll get very quick at identifying all of the forces acting on any object. So now some common types of forces. This is different than the list of forces I would give you in a conceptual physics class or even AP Physics 1 because different forces are necessary in different units. In this first unit in AP Physics 2, where we're dealing with pressure and buoyancy and fluid dynamics, we're going to be dealing with mostly these forces. At least as I look through problem sets and think about it, these are the forces that are most prevalent. So number one, the most obvious one, is the force of gravity. So if you're standing, gravity is always pulling you down. The force of gravity, also known as the weight of an object, is always pulling the object, at least on Earth, towards the center of Earth. If you were on the moon, it would be towards the center of the moon. But whatever planetary object you're on, that's the direction the force of gravity is acting. And we will discuss exceptions of that when we get into electrons, but that's not until much later in the year. Actually, that's AP Physics 1. Sorry. The way you calculate your weight, the way you calculate the force of gravity, is you multiply the object's mass times the acceleration due to gravity. So I feel like I should define those two terms. And before I go any further, I'm going to say the one thing I meant to say before, but I'm a fool, so I forgot. I want you guys to use this video as well as you possibly can. If you want to take notes on what I'm saying, feel free to do so. If you need to pause and rewind, obviously do that. You need to figure out how this video will work best for you. So that's something that I hope that as we go further and further on, you're like, okay, I want to do this, I want to do this, I want to do this. So play around with it, see what works for you. All right, back into the physics. To calculate the weight, it is your mass times gravity. And mass is all of your atoms, all of your particles added up together. That's all your mass measures. And that is measured in kilograms. And gravity, that's acceleration of Earth's gravity, acceleration due to gravity on the surface of whatever planet you're on. All of the buoyancy problems that I have seen deal with Earth's gravitational pull. So we're going to use gravity on Earth's surface. But if you were on a different planet, it would be the exact same thing, except you would use whatever gravity is provided for you on that planet. On Earth, gravity at sea level is 9.80 meters per second faster every second, or 9.8 meters per second, which means if you're falling, after 1 second, you're going to be going 9.8 meters per second, 806 meters per second faster every second you fall. Because that number is only accurate without air resistance, and because that number is only accurate at Earth's surface, or at sea level, any higher and gravity is going to get weaker. If you go down into a ravine below Earth's sea level, it's going to get stronger, which means rounding it or using such a precise measurement of gravity is ridiculous. Similarly, 9.81 is also an unnecessary, inaccurate number. If we're going to round to a number that's super easy to work with. And the College Board exclusively rounds to this value of 10 meters per second faster every second, or slower if you're going up. This makes your math so much easier throughout the year. If you drop a ball, as soon as you drop it, it starts at rest, right? It hasn't started to fall yet, so its initial speed is 0 meters per second. After 1 second, the ball will have gotten 10 meters per second faster. So now it's going 10 meters per second, because it gets 10 meters per second faster every second. After 2 seconds, 20. After 3 seconds, 30. After 4 seconds, 40. All right, the second force we need to discuss is tension. You guys, I'm hoping, have heard the phrase, you can cut the tension with a knife. That should help you remember what a tension force is. A tension force is any force that is applied with a rope, chain, whip, pulley, anything like that, anything that can go slack, anything that you can cut is a tension force. And we represent that with F sub T. And notice how all of these are the force with a little subscript telling what it is. Buoyant force. This is the upward supporting force that a fluid applies to an object. So if you throw a child in the pool, as the child is in there, before they start swimming, the water will automatically try to push them up. The water is always trying to push you up when you're in the water. That's why if you stand on a scale underwater, you'll read as less heavy on that scale, because the water is pushing you up, meaning the water is balancing out some of your force of gravity, some of your weight downwards. So instead of all 200 pounds of me standing on the scale, I have 200 pounds down from my weight, but the water might support 100 of those pounds, so I'm not as heavy, at least according to the scale. I still weigh 200 pounds regardless of what the scale says. So the buoyant force is the supporting force a fluid applies upward on an object. And side note, somebody asked this in class, yes, air is considered a fluid, but air is so non-dense, I don't know what the word for that is, but so non-dense that its buoyant force is fairly negligible. It's really small, it doesn't contribute a whole lot of anything, but it does exist, so that's kind of a fun thing to note. So in a vacuum, you would technically weigh a little bit more, because the buoyant force from air would be non-existent. So, and this is me guessing, instead of weighing 200 pounds, I might weigh 201 or 202 pounds. I would actually have to do the calculation to figure out how much buoyant force Earth's atmosphere pushes up and supports me with. Spring force. This is the supporting force any spring will provide. Spring scales that we use in class, they look like this. They have a little thing inside, and they have a little hook on the end, and you can hang an object from them, and this might read, I don't know, let's say it reads 20 newtons. It has a spring on the inside, and it reads whatever. If we look at the direction the spring is pulling it upwards, and I'm going to denote that F-sp for spring force. That is an upward force that is equal to 20 newtons. And I want to point out that if the force is up, it's going to be positive. If a force is downward, it's technically negative. So if we look at the force of gravity on me, because it's downward, it's a negative 200 pounds. I would have to convert that to newtons, and I'm not doing that in the middle of a slideshow. So up is positive, down is negative. Similarly, right is positive, left is negative. Just like in math class, you guys have all seen that grid, positive, negative, positive, negative. And you could switch them. I don't care, as long as you're consistent throughout the entire problem. So you could have negative up, positive down. As long as you carry that through your entire problem, I am absolutely okay with that. I think it's confusing as the dickens, but you're welcome to do it. So to make your life easy, ignore everything I said in the last 2 minutes and just know up is positive, down is negative, right is positive, left is negative. All right, so let's do a couple of example problems where we draw a free body diagram. Number 1, a ball resting on the ground. If you guys want, I encourage you to pause the video before I start each one of these and see if you get it right and double check. And we're back. So the forces acting on this, the normal force upwards and the force of gravity downwards. It's as simple as that. And now let's work through the other 3. Again, feel free to pause at any point and work through the example problems. Take 2 seconds, draw it out, see if you get it right. If you do, then you're set. If you're not, then you need more practice with forces problems. If you fall in that camp, talk to me, and I'll give you more practice problems. I will work with you on that. But if you can't draw force diagrams, you need to practice that so that you don't get lost. That's a really essential part of AP Physics too. All right, a hanging apple. Again, feel free to pause here if you need to. And we have 2 forces acting on it. Tension up and its own weight downwards. Number 3, a falling person. The forces we have acting on that, we have force of gravity down. Because I have weight, it's always pulling me downwards. My weight is 200 pounds. And again, all of your forces should be in newtons, but pounds is technically the English, not technically, it is the English or American measurement of force, the imperial measurement of force. Now, you could have also had air resistance acting on this person. So I'm going to draw air resistance up. And because you're falling down, the air molecules are bumping into you, pushing you upwards. Air resistance is 99% of the time working against the direction of motion. If you are running forward and wind is at your back, that would be one of the rare situations where air resistance is moving in the same direction as the movement. I hope I'm not going too quickly. If I am, rewind, watch it again, try to figure out what the heck I'm saying, and then ask me if it still doesn't make sense. I'm sorry. I'm trying to figure it out. All right, a floating pool noodle. So we have a floating pool noodle in the pool. We have the force of gravity down, and that force of gravity would be really, really small. Probably 2 pounds worth of weight, right? And remember, force of gravity is also known as weight. So if you ever see a problem where it says the weight of the object is vuja, then that vuja is the force of gravity. Force of gravity and weight are 100% synonymous. So we have force of gravity down and the buoyant force up because it is in a fluid. Cool. I need to slow down. All right, so now let's look at the forces acting on the following 3.4 kilogram object. I'm hoping that after the last slide, you guys should be ready to go and take a solid stab at it. Now, I want to point out there's a lot of things going on in this problem. There seems to be a scale at the bottom. There's a tank here. There's water here. There's a scale here. There's a ceiling here and a floor here and a string here and a box or block here. Whenever you draw your free body diagrams, only draw the forces acting on the one object. In this case, we are only looking at the 3.4 kilogram object. So take a minute, try to identify the forces. And hopefully, after you did that, you found force of gravity is down. Because it's being held by a spring, the spring scale is pulling it upwards. So we have the spring force up. And because it's in a fluid, we have a buoyant force supporting it as well. All right, so now we're going to take that exact same problem, and I'm going to relabel the forces. We have spring force up, buoyant force up, and force of gravity down. And now I want to calculate the force of gravity acting on it using that equation. This equation is also essential. That's how you calculate the weight of an object. Again, I already told you, but it's mass times gravity, and gravity on Earth is 10 meters per second per second. Whenever you do your work, I strongly recommend, number one, carrying your units through your work. It will catch you if you make a mistake along the way, because you'll start to recognize, oh, I'm calculating force, meaning my final answer should be a newtons or a kilogram meters per second per second. And I know if you're new to upper level physics, that probably sounds like a mouthful, like a lot of information, but I'm telling you, after you do 5 or 10 of these, that will become second nature to you. So we take the mass. Oh, and the second thing I recommend doing is always working your way vertically downwards. So we have 3.4 kilograms. That's my mass. And gravity on Earth is 10 meters per second per second. So then my final answer, you take the numbers, 3.4 times 10, and you get 34. My units, I just multiplied those as well. Kilogram meters per second per second. This answer is completely 100% valid. You can leave your units exactly like that is. Or you can get to the end and also realize, oh, wait a minute, it's a force and it's a kilogram meter per second per second. That's a newton. So the force of gravity of this object, the weight of this object, is 34 newtons. All right, moving on to buoyant force. I'm going to go ahead and jump right in to the equation and walk you through this. Again, we discussed the buoyant force is the supporting force a fluid provides. Anytime an object is in a fluid, there is a buoyant force acting on it. And it's 3 variables multiplied by each other. The more dense the fluid is, the more buoyant force you have. The more of the object that is submerged, the volume, the more buoyant force you'll have. And the stronger gravity is, the more buoyant force you will also have. And this should kind of make sense. If you have more dense fluid, like the Dead Sea with all of the salt in it, you will float more because there's more buoyant force supporting you. If you are in syrup, you will float better than you would if you were in water. Also, larger volume means a larger buoyant force. Mathematically, if you increase the right side of the equation, you're going to increase the left side of the equation as well. But logically, if you take an empty bottle and you push it under the water, it's easy at first, right? Because not a whole lot of volume is submerged. But the more you push it under, the more volume submerged you have, the more that water is trying to push it back out, the more buoyant force you will have. So the buoyant force, whoops, even though I already have it written over there, is the density of the fluid times the volume submerged times the value of gravity. Or this Greek letter rho, I think there's an H in it. I'm sorry if there's not. Rho Vg. So the buoyant force is equal to rho Vg. Gravity on Earth, again, 10 meters per second squared. Now here's something that is probably fair to expect of you. Water's density, or the density of H2O, is equal to 1,000 kilograms for every cubic meter. And remember, a meter's 3 feet. So if you have a meter box, 1, 2, 3, and you fill it with water, it will have a mass of 1,000 kilograms, aka super heavy. All right, so now that we've and it's also 1 gram per cubic centimeter. That one you will use less because in physics we use kilograms for mass and meters for length. So this 1,000 kilograms per meter cubed is the much more relevant equation. All right, so also know that density, rho, is mass divided by volume, which makes sense because density is how packed together the molecules are. The more stuff you have packed into a space, the denser it is. So it's the total mass divided by the total volume. M over capital V. And if we look at the units, that makes sense. Kilograms per volume cubic meter. All right. Now I'm going to go back to something I discussed with my 9th graders extensively. What are the 3 ways an object can accelerate, speed up, slow down, and change direction? If you guys don't have that burnt into your brains, I strongly encourage you make a flashcard with that on it. I also would add to that flashcard that the density of water is 1,000 kilograms per cubic meter. I don't think there's anything else in here that should be on a flashcard, but if there is, I'll let you know. All right, so in 9th grade, I drilled this into my students. And at the time, it had great value for recognizing acceleration, but now in higher level physics, it's not just because you want to identify the acceleration, but the acceleration matters because it tells you if an object has balanced forces acting on it or if the forces acting on it are unbalanced. So with a soccer ball on the field, we had normal force up and the force of gravity down. So I'm going to ask myself, anytime I see a problem, is the object accelerating? Let's break it down even more than that. Is the object speeding up? No. Is the object slowing down? No. Is the object changing direction? It is not. And because it's not speeding up, slowing down, or changing direction, it's not accelerating. If it's not accelerating, the forces are balanced, meaning this upward force has to perfectly balance the downward force. So the normal force is equal to the force of gravity. That's a big concept. That's super important. We could have also done it with the normal force, because it's upward, it would be positive, plus the downward force, or minus the force of gravity. They're going to have to balance out, so they're equal to 0. And really, that's the same as this equation, except I brought the force of gravity over to the left side of the equation. So normal force minus force of gravity equals 0 mathematically. Whew. Now, this brings a new term, equilibrium. If you don't have this word in your head, I would also make a flashcard for this too. Equilibrium means nothing other than the forces are balanced. So forces are balanced, meaning the total force or net force acting on it is 0. Net force, I wouldn't even say you need to create a flashcard for that because we're going to be using it so much. Now, I want to point out that net force is not a force on its own. Net force is all of the other forces added together. So do not ever draw net force on your free body diagrams. It's the total forces. All of the other ones added together. It does not get drawn on your free body diagram, ever. All right, so now we need to discuss net force, or the total force. And that's equal to, by the way, this is the equation, net force equals mass times acceleration. This Greek letter sigma just means total. So the sum of all of the other forces is equal to mass times acceleration. And this is where we're really going to use up as positive and down as negative and add them together. Fg minus F, or Fn minus Fg equals ma. And we'll work through a couple practice problems with that together. And again, m is mass in kilograms and a is acceleration in meters per second per second. So let's go through some example net force problems. For each of these, I want you to draw a free body diagram because it's good practice too if you don't already have that cold, and then draw a net force equation. And if you don't know what I mean by that, walk with me on the first one, and then you can do the other three on your own and double check in the video. So number one, again, we have the soccer ball resting on the ground. We've already labeled the forces before, normal force up and force of gravity down. But now we need to write the net force equation. Always start with that equation. Always start with net force equals mass times acceleration. And now the sum of all of the other forces, we're going to put them in here. We have normal force and we have the force of gravity. So normal force plus force of gravity, but also taking into account the signs. So normal force is up, so it's positive, and force of gravity is down, so negative. So normal force minus the force of gravity is still equal to mass times acceleration. Now, is this object speeding up? No. Slowing down? No. Changing direction? It is not. Which means it's not accelerating, or the acceleration is 0. That's why we care. Because if we know the acceleration is 0, 0 times any amount of mass is going to collapse to 0. And now you're left with Fn minus Fg equals 0. Now, if you kind of get it, but not completely, that's great, because we're going to do 3 more that hopefully will clarify that a little bit. All right, so number 2, the hanging apple. Again, even if you don't get it right, I encourage you to pause, do it on your own, and work your way through the net force equation. So we have tension up, force of gravity down. And now to do my net force equation, always start with your base equation. Net force equals mass times acceleration. Fill in your net force, or all of your other forces taking into account positive and negative. Tension is up, so it's positive. Weight is down, so it's negative. Tension minus the force of gravity equals mass times acceleration. And again, anytime I see acceleration, I'm going to think, is it speeding up, is it slowing down, or is it changing direction? No, which means acceleration is 0, and 0 times any mass is going to collapse to 0. So tension minus the force of gravity equals 0. It's in equilibrium. It is balanced. I'm actually going to erase this so I have a little bit more room. All right, so number 3, we have a falling person. And for the sake of this one, before you jump into it, I'm going to go ahead and break the rules and say assume that there is no air resistance in this problem. Challenge yourself and see if you can work through this problem assuming there is no air resistance. All right, I'm going to jump into it. We have force of gravity down. And if there is no air resistance, that's the only force acting on the falling person. So now I'm going to jump into my net force equation. Net force is mass times acceleration. Always start with your base equation. Net force is the sum of all other forces. Well, the only one we have is the weight, which is down, so it should be negative. So negative Fg equals mass times acceleration. That's it. That's technically sufficient for this problem. Now, if you wanted to, you could remember, oh yeah, we know the equation for force of gravity. If you don't, I think it's on your equation sheet. But you'll learn it in a week's time with as much as we will use it. But it's negative mg, which is equal to ma. Now, if you have mass on both sides of the equation, we can divide both sides by mass, and it will cancel out on both sides. So acceleration is equal to the opposite of gravity. And gravity on Earth is negative 10. So the acceleration of a falling person, regardless of their mass, because it's always going to cancel out, is negative 10 meters per second per second. That's kind of neat, right? I think that's kind of neat. That's why all falling objects fall together. That equation right there is why, assuming there's no air resistance. If there is air resistance, that's not true anymore. I'm going to stick with that for there and move on. If you guys want to know more about that, let me know. Or you can plug air resistance into that equation and see how that changes things. All right, number 4 is a floating noodle. We have the weight down and buoyant force up. And then I'm going to jump into my net force equation. Net force equals mass times acceleration. Net force is the sum of all other forces. Buoyant force is up, so it's positive. Force of gravity is down, so it's negative. So the buoyant force minus the force of gravity equals mass times acceleration. At this point, you could plug in mg for Fg, but really, we're done here. That's it. That's the final equation for number 4. All right. So now I give you the challenge. We've done each of these steps separately. In fact, before you jump into this problem, I'm going to change this instead of 1 cubic meter to 0.0001 cubic meters because the problem won't work otherwise. I'm hoping that number is small enough that it will work. If it's not, I'm going to be really upset with myself. So work your way through those steps and then come back and check with me and see if you did them correctly. Or do each step once, check to see if you did it correctly, pause, go to step 2, check with me. You guys get the idea at this point. All right, so I'm going to start labeling the forces. We have spring force up. We have buoyant force up. And the force of gravity down. I'm hoping you guys remember that there's also a spring force in this problem. It's been a while since we've discussed that. So now we've labeled the forces. Number 2 is we need to calculate the weight. And for that, I'm going to use the weight equation. Fg equals m times g. We know the mass is 3.4 kilograms. And we know gravity on Earth is 10 meters per second per second. And we're going to take the numbers, 3.4 times 10, and we're going to get 34. And we're going to take the units, kilogram times meter per second, and you're going to get kilogram meters per second. And I'm sure at this point you guys are getting tired of hearing me say that. So I'm just going to now say 34 newtons. At this point, I think we can save a little bit of time by doing it that way. So 34 newtons. So now we have the weight. Now you need to write your net force equation. Net force is equal to mass times acceleration. And now we need to fill in our forces, the sum of all forces. We have the buoyant force up, positive. We have spring force up, positive. We have the force of gravity down, negative. So the buoyant force plus the spring force minus the force of gravity equals mass times acceleration. And because we know that the object is not accelerating, we know the forces are, because we know, it's not speeding up, not slowing down, not changing direction, we know that the object is not accelerating. So the acceleration is 0, so the entire right side of the equation collapses to 0. So we have the buoyant force plus the spring force minus the force of gravity equals 0. And now we've worked through our net force equation. D, assuming it is a cubic meter or a 0.001 cubic meter object in the water, we need to calculate the buoyant force. So to calculate the buoyant force, hopefully you guys have looked back up on your own to try to solve the equation yourself, but it's the density of the fluid. And be careful, because in a lot of problems they'll give you the density of the fluid and the density of the object, and it's on you to know that you need to use the density of the fluid. Don't fall for the red herrings. It only matters how dense the fluid is for how much it's going to support, which makes sense. The denser the fluid, the more it's going to support, the more buoyant force it will have. So it's the density of the fluid times the volume submerged, not the volume of the entire object, the volume submerged times gravity. We know that it's in water, so that means we also know the density of the fluid is 1,000 kilograms per cubic meter. And we know the volume of the fluid is 0.0001 cubic meters. And we know gravity on Earth, 10 meters per second per second. Now I'm just going to take my numbers. 1,000 times 0.0001 times 10. Thank God I chose a small enough density, or a small enough volume. And we are going to end up with, is that 1? 1,000th times 1,000 is 1. Meters cubed is going to cancel out with meters cubed because 1 is in the denominator and 1 is in the numerator. And the only units we're left with is kilogram times meter per second, which is also known as 1 Newton of force. So now we have the buoyant force. And now part E is asking us what the scale should read. So now let's calculate the reading of the scale. To figure out the reading of the scale, the only equation we have with it in it is our net force equation. So we're going to take the net force equation and plug in what we have. Buoyant force plus spring force minus the force of gravity equals 0. We know the buoyant force is 1 Newton. We're trying to solve for the spring force, so we still don't have that. Don't forget that minus sign. We know the weight is negative 34 newtons. And we're going to bring this to the right side of the equation, and we're going to bring this to the right side of the equation. Or you can combine them first and then bring them over. But we're basically going to subtract 1 from both sides and add 34 to both sides, and that should be 33 newtons for your spring force. And that walks us through the entire first half of fluids in one PowerPoint. It was a lot. So if you guys made it through that, you did awesome. Please let me know what part of this video works and what part doesn't. Please let me know what part of class works and what doesn't. Because I'm lost. And I'm trying. And I need advice and I need suggestions. And I am happy for all of them. If you have questions on the content, please let me know. The sooner you get it fixed, the better. And aside from that, thank you guys for sticking with me through this entire video. I know it was long. I don't know how long yet, but I knew it was long. We're going to figure it out. And this is going to be a fun year. Because I do love these units, and I do enjoy you people. So, I don't know. We'll figure it out. Thanks for watching. I'll see you next time. Bye.